frequency scaling and everything it takes in order to measure performance and compare that with a simulator. And the results were kind of good. So they are reported here on the bottom of the slide. And essentially, we went a little further with that, up to that day where we're still busy doing such kind of things, well, part-time, of course. But essentially, what we do is that we use some real hardware, like, well, that's the era of single-board computers, like the Android XU3 that you see there. And on the basis of that, we calibrate a Gen5 model, like this is a big. LITTLE architecture, for instance, and we use, well, at the time, we had no option but to use MacPad, so of course, that's certainly not the best solution those days, but we did use that. And once you have a modeling, performance and power modeling of a given system, then you can go ahead and try to explore the performance of a new non-existing configuration. So here I'm showing here on the right-hand side of the slide some possible big. LITTLE inspired configuration that may be asymmetric or big, medium, little kind of configurations. And of course, because the focus of the project is power efficiency, then we try to, well, for a given application using a given API, try to figure out what's the best architectural trade-off in terms of performance and energy efficiency. Then we soon realized at the time that Gen5 were not ready for many cores. It's way too slow. We know that. You've all heard that before. And of course, there's always this question of the trade-off between the speed and accuracy. So here, of course, well, Gen5 would be somewhere here with cycle approximate model. At the bottom hand, you have just-in-time compilation. We heard about that in the morning, such as solutions such as OVP. Essentially, what we thought at the time was like, let's try to use Gen5 and bring the principles of trace-driven simulation in order to possibly achieve up to an order of magnitude speed up in the simulation of, in the simulation performance. And that happened to be a quite good idea because one of the first things we did at the time was to do a profiling of a Gen5 simulation, such as to understand where most of the simulation effort is being put by the host workstation. And it happened at the time that, well, at the time it's still the case now, and that's maybe even worse, that about 70% of the simulation effort is put into simulating the cores themselves. Therefore comes the idea of defining what trace-driven simulation could be with Gen5 on the basis of that representation that you have here on the screen, where you see that essentially when the CPU runs some code, then it's like those TC1, TC2, and so phases. It's not depending. It does not depend on the performance of the interconnect and memory subsystem. Yeah. What depends on the interconnect is when there's a cache miss, and then you have to go all the way up or down to the memory and wait for the response to come back. So essentially, here those blue circles you could see them as like those events that are put in the Gen5 event queue. And essentially, the idea would be to, since those times gaps remain constant in all the processors at least, then let's wipe them out of the simulation and do actually focus the simulation effort on the memory and interconnect subsystem. And that's essentially what we did with SimMate. That was published back in 2012, I believe. So that's a two-stages process. On the left-hand side, you have the trace collection, where essentially you run a full system simulation. And what you do is that you perform a trace record whenever there's a L1 cache miss. That's only at those points that you do record something in the trace. And then once this is done, then you can go ahead with replay, where you just remove the processes, the cores themselves, and you replace them by trace injectors, like they are represented here in green on the right-hand side of the slide. And essentially, it makes it possible to boldly speed up the simulation. So when you're doing that, well, it makes it possible to do some fast design space exploration on a number of parameters, but still, when you collect a trace, you somehow do a snapshot of what the system is doing, right? So there are some parameters that are frozen, and there's no way a trace-driven simulation can account for changing those parameters. So those parameters that cannot be changed any further are those that relate to the CPU, and those that relate to the private caches, the L1 caches. But all of the rest, so that's depicted here in red on the slide. I don't know if I have the mouse. Yes, here, that's better. Everything that is in red here on the slide can be changed, and then you can run a simulation without requiring to recollect the traces. So this is a representation of how it's being how it works. Essentially, you see that here you have the trace injector, the caches, and then the memory interconnect subsystem. And here we do assume that we're talking about a memory subsystem that is a little slower to that we used in the trace collection. So here, if it happens that the memory subsystem is a little slower, then the response is going to arrive a bit later compared to what we had in the trace at tracing time using the full system simulation. Then the only thing that we do is that just shift everything forward in time so as to account for this additional latency that is incurred by a slower interconnect. And this makes it possible to, well, do some pretty good, pretty accurate performance estimate on what is the impact, the influence of a faster memory or a faster interconnect or whatever. You can even change the L2 cache size. So what I'm showing here is an experiment on the, well, changing the DRAM latency. So we were using at the time, that was the only one available at the time, the simple memory model with 1 unit latency and plus a spread kind of a parameter. So we did run the trace collection here with 30 nanoseconds for the latency of the external memory. And then we've changed in trace-driven simulation only that parameters. And then we always compare that to the full system simulation reference. And the results that we obtained were pretty good. That's always single-digit error that we obtained. And then the speed that we had with that was 1-2 orders of magnitude. So that was pretty good. Well, you could do this pretty much the same with the L2 size, changing the L2 size. Here, that's not as good as it was for the interconnect. The reason for that being that when you're collecting the trace, you do that without any L2. So when you rerun the simulation with an L2, you have to deal with a cold start bias, well, cache warm-up kind of parameters. So ET is only the execution time of the application when you start tracing the application, when you actually render in the RCS, start the application. But if you encompass the initialization and even the operating system boot, then you're improving the accuracy. But still, that's not perfect because of that cache warm constraint. All right, when you have such traces collected, it makes it easy to perform the so-called, even that's not fully accurate, trace replication. So essentially, you have a trace for 2 CPUs, and then you can emulate a system that has not 2 CPUs, but 4 CPUs by means of putting 4 trace injectors. And then you replicate the traces that you had collected on 2 cores onto 4 cores. When you do that, it's called weak scaling because essentially the workload per core remains the same, and it makes it possible to go further and do such kind of experiment with scalability kind of experiments. Yet, if you do that, you have to take into account the synchronizations because there's always an underlying API, project thread, OpenMP, whatever, and there's always synchronization. So I'm not going any further with that because I have details on the current work on it, but essentially it relies on having a trace arbiter that makes sure that whenever a thread reaches the barrier, in trace-driven simulation, then it goes no further up until the other thread reaches the barrier as well. So that's the principle. One main limitation of what we did at the time was the fact that this was okay for in-order processes only, of course, because there's this nasty assumption that the compute time remains the same between 2 cache misses, and this does not apply to, of course, out-of-order processes. And that's overly important because one of the objectives that we have in the project is explore heterogeneous architecture such as big. LITTLE kind or big. LITTLE inspired architecture, showing here the Helio X30 with 3 core families, 3 clusters, and we are deeply interested in those systems. And what's the difference in those systems is the actual microarchitecture between one cluster and the other. So there happens to be an interesting contribution by ARM and the University of Kaiserslautern, which is elastic traces, which is essentially bringing down the principle of trace-driven simulation at the microarchitecture level. It's closer to the core. And essentially the spirit of that is you still do some tracing here with the O3 model, but you do not, when you do the replay here, you do not focus on trying to simulate the actual execution of the instructions, but rather to account for the dependencies between the instruction and the resource availability inside the core. So this is yet another snapshot from the Gen5 wiki web page that, I'm putting the link here, which is describing how it works, where essentially there's a dependency-free queue of instructions, And well, the runtime, well, the trace CPU picks those instructions out of this queue, and depending on the type of instruction, like if there's store, there's nothing to be done. If there's a load, then there has to, well, there's a request that is sent to the memory subsystem. And then when the response comes back, then you go all the way back here, and then you update the dependency graph, and therefore the dependency-free instruction queue, as long as the hardware resources, and then you go on up until the end of the simulation. This worked pretty well. And what we did within the scope of the project was to bring the principle of CMate, which was essentially enabling multi-threaded trace-oriented simulation with elastic traces. So here you recognize the I side and D side generators that are themselves reading records out of their respective traces, the instruction and the data dependency trace. And what we did was adding another trace that actually records all of the information concerning the barrier. So I'm taking yet again that example of multiple threads that are running on multiple cores. When there's a thread reaching the barrier, you want to make sure that you go no further up until all of the other threads have reached the barrier. So essentially, this is done by means of having a kind of arbiter that keeps track of the progress of all the trace CPUs, and then it locks the trace CPUs one after the other when they're reaching the barrier, and when all of them have reached the barrier, then it unlocks all of the trace CPUs. Yes, so the difficulty is doing some proper tracing of the synchronizations for this kind of software, and we use the OpenMP because that's one of the most popular APIs. We're using 3. Parallel 4 kind of construct, and essentially, I'm giving you a very conceptual overview of what's happening on a workstation when it's running some OpenMP code from the source code that is depicted there. When you run the compilation, then the preprocessor embeds directly calls to the runtime here. So that's here again abstracted away as an OpenMP runtime call. And then it creates a binary. This binary calls at runtime, the OpenMP runtime, and the scheduler. That takes care when reaching the power region to create threads onto the cores that are available in the architecture. So this is the abstract representation of the timeline of the execution of the thread, and what we're actually interested in is inserting some trace records at those points here that are depicted here in green. And then each record essentially records the PC, the tick, the type of synchronization, the thread ID, of course, and the number of instruction and data dependencies that this power region is made of, because that's going to be reused later on. So in order to do that, so that's a kind of wrap-up, so I still have same kind of code. We use the BSC Mercurium compiler together with NUS++ runtime. We've tweaked the runtime a bit, such that whenever there's a call to the runtime, so that's depicted here, then there's a call to a custom pseudo instruction, or M5 pseudo instruction, that actually creates a trace record and makes it possible to actually trace the execution of the application and the synchronization without actually modifying what's happening inside the simulated architecture. It generates all 3 traces, and then you can go on with the replay. So there are 2 main use cases, the fast parameter exploration and scalability study, and the question is, speed up and accuracy. So I've decided to still show some results here, even though that's still a work in progress, and there's still we're still unhappy with some of the accuracy figures that that were reported by the simulation, but still I'm showing that here. So we're expecting something better at the time, but here what you're seeing here, FS is full system, so that's the execution time with different cache sizes at replay time, and ET, elastic trace, ESM, so that's elastic CMate, is in red and green here. Of course, you see that the predicted performance by elastic trace and elastic CMate is about the same. It's normal because it all relies on elastic trace. And then we have results for a number of applications here. So like I said, we're still trying to improve the performance. Of course, you have access to all of the statistics, execution statistics. So here you can keep track of what's happening concerning the miss rate on the L2, or even the miss latency, everything that does not actually relate to the core, to the processor itself. It's accessible. One of the main interests, of course, is doing the trace replication for scalability analysis. So here again, we do replicate to an extent the traces, and these are some of the results that we've obtained. So here on the left-hand side, you see for three applications actually, the execution time versus number of cores are all the way up to 128 cores, and then this is the simulation time, so the time it took for Gem5 to provide to complete the simulation. And essentially here we have simulations that are lasting minutes, inside the simulated system, and the simulation itself lasted hours. So it's acceptable in terms of simulation performance. You can explore system sizes that are pretty large without having to wait for weeks up until you have an estimate of the performance. All right, so this scalability analysis has bold limits. I have to say that. First, these are things I didn't mention. It requires some additional features, such as address offsetting. If you stupidly replicate the traces from core to core, what is going to be happening is that all of the cores that use the same trace are going to be firing requests to the exact same memory addresses, and therefore, we're going to have a very happy L2 cache that is going to be showing a very high hit rate. So what you have to do is to offset the addresses, which we did, in the different cores, such that you can observe some realistic performance figures. And again, what we do when you do that, that's weak scaling. So weak scaling is of lesser interest because essentially it tells you when you if you have twice the number of processes, it tells you how long it's going to take if you have an problem that is twice bigger. And you would rather be interested for the same problem size, what's going to be the speed up if I'm having twice as many process cores. So that's the most interesting thing. And it happens to be that in the programming model community, and that's also something that is boldly explored in Mont Blanc project, in the Mont Blanc project, that's the fact that the programming models like OpenMP and OMS, which is a kind of forerunner from BSC, are moving from loop-based parallelism to task-based parallelism. And essentially, some of you may already be familiar and even know more than myself, but essentially the principle is declaring tasks and declaring what are the inputs and outputs of those tasks, such that at runtime, you have the OpenMP or whatever runtime that is capable of building a dependency graph for all of those tasks and have a ready task queue that assigns the ready tasks via a scheduler on all of the processing cores. So there's a massive amount of parallelism that is available compared to basic loop-level parallelism, and it happens to be a very good opportunity because that's going to be becoming at some point mainstream. That's in OpenMP4, 4.5 will go even further. That's a very good opportunity for trace-driven simulation. Why that? So here I'm representing once more what we could do in trace-driven simulation, and the principle here would be rather than tracing the behavior of the CPU cores themselves, we actually unbind the traces from the cores, but we try to trace the tasks themselves. So it means that here, what we would do is try to know when a given core is running one given task and capture this task trace. Then we have a trace chunk that belongs to one given task, and then we build a library of all of the tasks that have been assigned to all of the cores during the execution, such that at runtime, then you can have a ready task queue, pretty much the same thing, and a scheduler runtime that is emulated like at the Gem5 level, not inside the architecture, not in the application or system software. At the Gem5 level, that replicates the kind of behavior that happens on the realistic system. And then it assigns dynamically the traces from the ready task trace queue to the cores themselves. And by means of doing that, it actually makes it possible to do strong scaling kind of experiments, so benefit from the massive speedup that trace-driven simulation provides, and yet have a strong scaling kind of performance analysis. So that's pretty well. That's one research direction. So that's one perspective. We're still trying to come up with the concept, lay down the foundations of the concept. So this takes me to the conclusion of that presentation. So we have a current ESM prototype, so I'm using the prototype keyword because that's still work in progress. We're still trying to figure out what's happening and track down the bugs. We're in contact with the ARM in order to find what's happening inside the elastic trace that makes the simulation a bit off for some corner cases. So here showing some result where we're boldly off. But still, we expect that to be fixed in some months. At some point, we hope that this is going to be integrated in Trace CPU. It's going to be submitted for review to the Gem5 board. In terms of use cases, of course, we can perform exploration of the memory system, and we can even, because there's elastic trace behind, explore some of the possibly covered microarchitecture parameters. And there's a bunch of future research directions, such as it's not compatible with Ruby or Garnet yet. That would have to be done because it makes no sense to run the simulation of a system that is made of 128 cores if you have a simple memory or simple interconnect. Yeah. It could even be combined with some other initiatives such as this Gem5 for further speed-up benefits. And it can easily be extended to other APIs because essentially we're just keeping track of the dependencies, and it can be easily done when you're tracing the application execution. So with this, I'd like to thank you, and ready to take any question if there's.
Do you have any questions? We have some time for questions. All right.
Thank you.
James.
Thank you.
He has interned with Qualcomm Research, Silicon Valley, and received the Roberto Padovani Scholarship for his outstanding technical contributions. In addition, he has been recognized at the university and department levels for excellence as a teaching assistant. His research interests include performance evaluation in computer architecture, heterogeneous architectures, and multi-threaded workloads. And one additional note that this topic that Mario is going to tell you all about is a collaborative project between research group in ARM, the Architecture and Technology Group, and the University of Toronto. So it's my pleasure to hand over to Mario.
Thank you, Radhika. Good afternoon, everybody. Thank you for coming. I'll be talking to you about generating synthetic traffic for heterogeneous architectures. In many ways, this builds off of a lot of some of the previous presentations, like the one we just saw on traces, as well as the Garnet, for example. So I'm going to be leveraging a little bit of what they talked about. So first, let me discuss what synthetic traffic actually is. If you already know the answer to this, bear with me. So I'm not talking about synthetic traffic as the case of, for example, uniform random, but more so synthetic traffic that actually represents a real workload. So if we had a real workload and we were to run it on a heterogeneous system, we would get some results that tells us how well that application ran. We could also generate a trace, and we saw how we could use traces to speed up simulation in the previous presentation. But what we can also do is create a statistical profile of that trace. And then we can take that statistical profile, and Gem5 has this traffic generator that will then synthetically create traffic based off of the profile and inject it into another heterogeneous system. So the key thing here is that we have maybe one trace or a handful of traces that generates this statistical profile. And then using one profile, we can evaluate many heterogeneous systems at once. And the goal is that the results that we get from the statistical profile are similar to the ones that we get when running on an actual system or a simulated system. So in this talk, I'll be talking about our contributions, which are still a work in progress. They're not in Gem5 yet, but we hope to have them there in the future. So there's the arrow now going from the trace to the statistical profile. So right now, there's nothing that currently does this. So we're going to come out with a tool that will generate a model or a statistical profile based off of traces that you see. And then we're doing some extensions to the traffic generator in Gem5 to accept these models and accurately generate synthetic traffic. So what do I mean by a heterogeneous system? A lot of you already know about the CPU and the GPU. There are also other accelerators. In this talk, you'll see things like the video processing unit, VPU, and display processing unit, DPU. Okay, and these would all be connected to an interconnect. In this case, we're talking about a cache-coherent interconnect. You could potentially connect it to Garnet and have that stimulate a coherence protocol from Ruby, for example. We're not looking at that yet, potentially in the future. So why synthetic traffic? So in the last talk, we saw why we would do traces. But synthetic traffic actually allows us to distribute models instead of traces. So sometimes those traces are proprietary. Sometimes those traces are multiple gigabytes large. It would be difficult to provide these traces to other people. So this way, we can actually distribute models. And if you have the model, you could potentially modify it. So if ARM tells you this is what a VPU sort of behaves like when running this workload, you could say, okay, well, what if I wanted to increase the number of reads or increase the data size with each message? You could tune the model to what you want to sort of see. And then finally, we can also converge quickly to a final result. So the theme in Gem5 has been trading accuracy for performance. This is one of those ways. So because this is a profile based on distributions, those distributions tend to converge. Once they converge, why don't we just end the simulation? There's no reason to keep going. So what does a statistical profile need to capture? So let's answer a few questions. So what kind of message should be sent? So writes and reads will have very different impacts on memory and the system itself, so we should be able to track that kind of stuff. In addition, when should this message be sent? So we should be able to track periods of idleness or bursty behavior, and how can we do that? How big is the message, right? Different messages have different packet sizes associated with them. Is it a data packet? It's probably going to be larger. Is it a control packet? It will be smaller, right? And then where is the message going? So a lot of times where the message is going, the destination of the message is based on the address, right? So based on the address, we can determine which memory controller we actually have to go to. So these are all great, and if we took a trace, we looked at the entirety of the trace, and we characterized them based off of the answers to these 4 questions, that would give us one answer that sort of averaged out a lot of the variability in the trace. So what we also need to do is we need to answer how do these statistics change over time? Okay, so one potential statistical profile, this is quite similar to what you see in Gem5 at the moment with a few slight changes. But what kind of message should be sent? We can just calculate the percentage of reads, and then 1 minus that is the percentage of writes, and then just use a very basic distribution for that. When should a message be sent? So we can model that as a Poisson distribution, for example. So find the time between events, what's the average time between events, and use that in a Poisson distribution. How big is the message? So you could use a distribution for the data size, or potentially just the average, depending on how much fidelity you want. And then where is the message going? So I'm not going to talk about this too much in this presentation, but address synthesis is extremely important. So for example, you could take the minimum memory address that you've seen and the maximum, and then generate addresses linearly through that or randomly within that range, et cetera. And finally, how does it change over time? So we've seen a lot of work, like for example, SimPoints, Smarts, et cetera, on how there's time-varying behavior in applications. So if we can represent one of those phases as a state and then have a statistical profile for each state in the application, then we could potentially model the transitions between them. So this is a very crude look at how Gem5 sort of works at the moment in its traffic generator. As time gets updated, we check, should we be injecting a packet? When the answer is yes, we find out when the next time we should inject the packet is, and then we inject the packet. So the next packet tick function would use something like the average delta time that we saw on the previous slide, and then the get next packet would use things like the read percentage, the average data size, et cetera, to generate a packet to inject into the network. For time-varying behavior, we have a little bit more complexity associated here. So we now need to determine how to transition between one state and another. And when we do so, we then use the statistical profile associated with that state. So let's talk about how we go from a trace to a profile. So first, we're going to divide the trace into a series of intervals. Then we'll group intervals that are similar to each other, signifying that these belong to a type of phase or state. Then we'll model each of these states, and then we model the transitions between each of those states within the trace. So here's a look at a GPU workload. On the y-axis, we have time. Time is represented as intervals. Each interval is 100,000 cycles. On the y-axis, we have the total number of messages being sent. So we can see some sort of time-varying behavior here, which is really cool. And what we can also take a look at is what if we created a statistical profile for every single one of these intervals? Okay, so let's do that. So the first 100,000 cycles, I see that I'm getting 100% reads. In the next 100,000 cycles, I'm down to 72% reads. In addition, the time between the events is more frequent in the second 100,000 cycles, right? We have an average delta time of 27 cycles. So that implies that there's going to be more messages sent, and that's what we see on the y-axis. So if I was to create a statistical profile for every single one of these intervals and then replay these profiles in the sequence that you see them here, right? So in a trace, we would replay the events as we see them. In this case, we're replaying the intervals as we see them. What kind of results would we see? So here's the interval replay results. I have megabytes per second on the y-axis. We're looking at bandwidth. And in blue is what you'd get with a trace, and in orange is what you'd get by replaying the intervals with the profile. And we can see that we're capturing the bandwidth with a pretty decent fidelity, and this is for a variety of devices, CPU, DPU, GPU, VPU, and each one is running one or more benchmarks, so this is the average of those benchmarks. They're not running concurrently. Okay? So we can get pretty good fidelity in terms of bandwidth just by replaying the intervals. Of course, that doesn't give us any speed up, really. We might as well just replay the trace. So now let's work towards getting that speed up. So we can group intervals using something like clustering. So we saw clustering, hierarchical clustering in one of the previous presentations. This is k-metoids. So k-metoids, I've provided a k of 3 to give us 3 groups. And you'll see that the least messages sent are in green, the most are in yellow, and in between is in orange, assuming the colors show up properly. And then because we're using k-metoids, we can actually find out what the most representative interval is for a group, right? So for the green group, which one is the most representative interval? So here with k-metoids, we find that we have orange, green, and yellow corresponding to these intervals as the metoids. And we see that each one has a pretty different statistical profile, right? We're looking at 52% reads in orange versus close to 100% in green versus just under 40% in yellow. And other things are different as well. So using these metoids, in the previous, some of the previous slides, what I showed you was we replayed the intervals. So that was the top graph here, the original observed data. So rather than replaying the intervals, rather than creating 27 statistical profiles for every single interval, let's just use the 3 that we did when we clustered. And when we replace the groups with the metoid interval, right, we still get some time-varying behavior. It's not as variable as the original observed data, but it still does change, and unless you take a close look, it looks relatively similar. Okay? So now what if I replayed these 27, the bottom 27 intervals here? So I only have 3 statistical profiles that I'm replaying in this sequence. Once again, my bandwidth is still relatively similar. Okay, but once again, I have not received any speed up yet. I'm still simulating for the exact same number of cycles. So how do I converge early? How do I get to a result early? Well, I can take a look at the sequence that these metoids occurred. So, for example, it goes green, then yellow, so on and so forth. And I can build a Markov chain based off of that. So here we see the Markov chain, and there's the transition matrix to the right. So the orange state is state 0, yellow is 2, green is 1. Okay, so if we look at the top left part of the matrix, we'll see that state 0 transitions to itself 60% of the time, and transitions to state 2 33% of the time. Okay, and if we look at the observed sequence of metoids, that seems to be pretty reasonable. So this looks correct. Then what I can do with a Markov chain is that a Markov chain, after it goes through a few iterations, it tends towards a steady state. Okay, so there's a formal way to get this steady state, but we can approximate it by raising the transition matrix to an exponent. So here I've raised the transition matrix to an exponent of 512, and you'll see that each row of the steady state matrix is the same. So let's take a look at the top row. This tells me that I should be in state 0 58% of the time. I should be in state 1 19% of the time. I should be in state 2 23% of the time. Okay, so I have basically what I should be in before when I've reached steady state. So now, during simulation, if I am approximately, I can actually track which states I've been in, right? And when I'm approximately in those states 58% of the time, 19% of the time, 23% of the time, I can say, hey, I've converged. I no longer need to continue this simulation. Let's exit now. So the concept of close enough is a threshold that you need to tune yourself. So you can do that based off of like the chi-square test, or you could use other distance metrics. So here is the time to converge. So we can see that not all of the benchmarks here have converged early. So this means that we were a little too strict with the threshold that we chose. We could probably relax it a little bit. But some of them did converge early, and when they did, you could see the potential for significant speed up. So for example, Coast Guard pretty much had very little time required to be simulated. If we take a look at the bandwidth results for the applications that were sped up, we still have comparable in terms of fidelity bandwidth. This is total bandwidth for these applications. Okay, so we see that we can converge early and we can maintain the fidelity. All we need to do now is start tuning the threshold in order to get that to an appropriate number so that we can converge early for many more benchmarks. So what we're working on for the future is right now interval size and the number of groups are user inputted parameters. It would be better if they were not, because for different applications and for different devices, these things change. So if we can automatically determine those, that would be fantastic. In addition, how should the address be synthesized? So throughout this presentation, I just showed you bandwidth. Bandwidth is not the only metric that we're interested in. So for example, how different addresses arrive at the memory controller can impact performance. Some of them may be merged because they're already in the queue and stuff like that. So address synthesis is of paramount importance as well. Anyway, that's everything I had for you today. Hopefully this will be in Gem 5 soon, and then you guys can start playing around with it. Thank you. Yes?
So you consider just a fixed percentage between reads and writes. But for DRAM, for example, it's important when you have maybe an X as a read, and then after that a write, and again a read and a write, then you get a huge penalty because of the write-to-read turnaround time. Do you also consider this, or this could be also considered in such a model?
Yeah, we haven't considered it yet, but that's definitely a good point, and I think it would go with also the address synthesis part as well. So that's a very good point. And yes, so depending on how complicated of a statistical profile you want will also impact what kind of results you'll be getting.
And for now, you have always a window size which is fixed to 100,000 cycles. So would it be also maybe interesting to make them with a different size depending on what's going on in the system?
Yeah, so there's been a lot of work on variable-sized intervals versus fixed-sized intervals. I believe variable-sized intervals is the best. That comes with automatically characterizing how long an interval is, which is much more difficult to do. But for example, you can see here in the first 100,000 cycles, it was 100% reads. Well, how long was it 100% reads for? Maybe it was 100% reads for 120,000 cycles, and I should have chosen that instead. And also having variable interval sizes for each interval would be great, and that's the ideal. Yes?
Is other synthesis actually necessary? So can you come up with high-level metrics, for example, like if we're looking at working set sizes or I don't know, like DRAM topology?
Yes.
Come up with high-level metrics so that you don't have to synthesize the exact addresses.
So there's been previous work from AMD that extended the Sinful paper to do that based off of their model for DRAM. So it's a higher level model. It didn't see as good fidelity as I thought it should. It's possible that a better model would be able to capture that. But there has been also work using reuse distance for address synthesis, and I'm going to try that, I think, first to see if I can actually get high fidelity there. Yes?
Can I ask a
Yeah, I'm not sure.
Jason, that one?
Yeah.
Can you talk a little bit about, and I think this is probably related to interval sizes, but how to deal with burstiness? I know like GPUs, for instance, are very bursty. They'll have hundreds of thousands of requests and then just sit there on it.
Yeah. So, so the AMD paper tried to tackle that as well, and they found that they were using an exponential distribution in order to send the packets. I believe the problem can be solved with, so here I'm just showing you one level, right? If I can start decomposing this into multi-levels, let's say two or more levels, each one with a finer granularity, I can start capturing that kind of burstiness, as opposed to relying on a Poisson distribution for 100,000 cycles.
I think there was also the FFT idea, isn't it?
Yes, and then also looking at frequency analysis to determine those kinds of things.
Have you thought about data sharing? So you have like different processing elements like the VPU, and the VPU might be preparing like a frame buffer which then display processors and display. Have you thought about like how you could actually coordinate? Maybe it's part of the address synthesis.
Yeah, I haven't thought of that actually, but yes, it would be part of address synthesis, and you would need traces sort of that demonstrate that kind of sharing, or you could potentially just say, so when you do the address synthesis, you could potentially have the same offset for each of these devices so that they actually share data. But I haven't looked at that. I don't know how complicated that would be.
Any more questions?
Thank you.
Okay, let's thank the speaker.
touch me, babe. I'm falling. Come save me, baby. I'm calling.
So next up, we have the story about Gem 5 and System C. And we have Matthias here to present it along with Christian, and I'll introduce both. So Matthias Jung, I guess, received his PhD degree in electrical engineering from the University of Kaiserslautern in Germany just this year. His research interests are System C-based virtual prototypes, especially with the focus of the modeling of memory systems and memory controller design. Since May 2017, he is a researcher at the Fraunhofer IESE in Kaiserslautern in Germany. Christian Mernard received a diploma degree in information systems technology from TU Dresden in Germany in 2016 and joined the chair for compiler construction as a PhD student within the Excellence Cluster CFAED in TU Dresden. His current research includes system-level modeling of widely heterogeneous hardware as well as data flow compilers for heterogeneous MP-SOC platforms. So I hand over to Matthias now. Thank you.
Yeah, thank you, Radhika. So this talk is about system simulation with Gem5 and System C and also other tools. And we have only half an hour, so we cannot tell you all the details, and therefore I encourage you to look at the paper and also in /utils/TLM in the README file. There you get an impression how exactly this works. So why is System C important? I have some slides here about virtual prototyping with System C. And these virtual prototypes that are used, System C based in industry, they are functional software models of physical hardware, and they provide controllability over the entire system and offer powerful debugging and analysis techniques. And a cool thing about all these virtual platforms is that we can reuse them for future projects. And what we can do as hardware engineers is fast design space exploration. That means we can try out different things like how big is my cache, or what is the number of cores that I should use. And it's easy to exchange. So if I build a FPGA prototyping board, then I have to send it in another country. This is more complicated. So here we have just software that we can email. And what is also important, that is for us in Fraunhofer Institute, is that we can already develop software before the actual hardware is there, and therefore we can basically make a shift left such that time to market is reduced, and at the end, hopefully also the product gets a better quality. So we have some use cases that we will show also later. On the left side, that's what's going on at TU Dresden also with NOC simulations. And on the right side, we see advanced DRAM simulations with DRAM sys. I will show you that later. Okay, about System C in general. System C is a standard from IEEE, and it's there for modeling hardware components and software components. And it extends C++ to an event-driven simulation kernel, and it has various levels of accuracy that it offers. And it's maintained by a group called Accelera. And the idea was, of course, to have 10 up to 100 times faster cycle-accurate simulations compared to VHDL and Verilog. However, so the normal cycle-accurate System C is still not fast enough to boot an operating system in a reasonable time. And that's the reason why they came up with the idea of transaction-level modeling. So here we see again a cycle-accurate model, which has on all the components a clock and is pin accurate. And we simulate on each pin the events that are happening. And then you know that you get these crazy waveforms, and you have to identify what's going wrong maybe. And on the other hand, what is TLM now offering? So instead of simulating all these bazillion events, communication gets abstracted with the help of function calls where we transfer references. And that makes the simulation, depending on the level of accuracy that you choose, up to 10,000 times faster than in VHDL simulation. So how does it work in general? So you could have a system like this with a CPU, a bus in between as interconnect, and then target memory and target I/O. And when you want to communicate now, you draw a so-called payload reference from a pool. And this is basically then a pointer to a payload object that has the information like command, address, data, and so on and so forth. And with function calls, you transfer this pointer to the target, then you do something there, and you transmit the thing back. So that's basically TLM. And you can already see that this is very similar to Gem5 behavior, and we will explain that later. Okay, just to give you a brief idea what TLM is, so there are several use cases. So you can model platforms with TLM that are just for software developing or software performance analysis. So that's what you see on the left side. And then we have architecture analysis and hardware verification. This is more for the hardware guys. And therefore you have basically two coding styles. One is loosely timed, and there it's using the idea of debug transport and blocking transport. And this debug transport is basically that what you have in Gem5, what you call functional. And blocking is that what you call atomic. And on the right side, you have the non-blocking transport, which is very similar to the timing access in Gem5. And therefore, you have different mechanisms. And I don't want to go into detail about them. But it's a standard, and if you stick exactly to the definitions there, you have a full interoperability. So if you get a model from another company, you just plug it together with your model, and it will work. Yeah, and therefore, TLM is widely used in industry. You can see that there are a lot of tools from vendors like Synopsys, Platform Architect, for example, but also other tools from Mentor and Imperas, and also a lot of models. So for ARM example, there we have the so-called fast models, and they have only this loosely timed blocking kind of TLM modeling, and it's based on JIT, and it's non-free, and it's a library, so you cannot change these models. Then we have also the Carbon models. So Carbon is a company that was acquired recently by ARM, and what they did is that they translated their HDL models into kind of System C models, compiled them, and shipped them as a library. So they are cycle accurate, so very accurate, but they can also not be changed. And then you have also models from Imperas. But they are free, but only loosely timed. So somehow there was a free, very accurate model missing, and therefore we had to look on Gem5. Yeah. Okay, I hand over to Christian now.
Yeah, so I'm going to show you how we can actually couple Gem5 with System C and then build a co-simulation environment. So actually, Gem5 already supported the coupling to the System C kernel. And I'm just going to show you quickly how that works. So when we look at Gem5, then it's basically an event-driven simulation kernel, and then some logic that models hardware. And now what we can do is we can compile Gem5 as a library and only use this logic. And we can link this to a System C project. And then what we have is a System C simulation kernel and Gem5 logic. And now what we need is something that couples these two. So this is why a module was introduced, a System C module, Gem5 sim control. And basically what it does is it replaces the Gem5 event queue with a hook to the System C event queue. So whenever you would schedule a Gem5 event, what happens is you get a System C event, it will be scheduled, it will be executed driven by the Gem5 logic. So this already worked a while ago. The problem with this is that there is no way of communicating. So you can hook your Gem5 to the systemc kernel, but you can't communicate to other systemc modules. And this is why we started to work on a transaction to TLM, so that we are capable of plugging in any other systemc model and hook it to Gem5 modules. Okay, so let's have a look at transaction models in Gem5. So as Matthias already mentioned, there is the timing, atomic, and functional models. And these correlate very well to the interfaces that we have in systemc TLM. So the timing model in Gem5 is very accurate. It provides a lot of timing details. And the concept is very similar to the non-blocking transport interface of TLM. Similar, the atomic model in Gem5 focuses more on fast transactions. It doesn't provide so much timing detail. And this correlates well to the blocking interface of TLM. And then there's the functional model, which is used for initialization, debugging, and so on. And again, there's the counterpart in TLM, which is the debugged transport interface. So what we can do now is we can create a transactors. So we already have external ports in Gem5, and we created external ports that connect to TLM. And then we created some transactor modules on systemc. And what we can do is we can hook the two together and transact from Gem5 to TLM and vice versa, by simply translating these interfaces, these systemc interfaces, to the Gem5 models and vice versa. Okay, so let's have a look at an example how this works. So we have a very simple system here. We have a CPU simulated in the Gem5 world. Then we have our transactor, and we connect this to a memory simulated in the systemc world. If you want to send a request now to the memory, what the CPU does is it will create a Gem5 packet, which has some metadata, like a command data, some data array and address and the size. And then it will forward this reference to the external slave. Now what happens is we need to translate this Gem5 request, the packet, to the systemc generic payload. So what we do is we create a new generic payload object, and then we copy all the metadata from the Gem5 packet to the TLM payload. Fortunately, the metadata is very similar, so we can actually just copy it. And now we need to keep track of the original packet that we generated this payload from. So what we do is we hook this reference to the packet as an extension to the generic payload. And now we follow the TLM procedure, forward the payload object to the memory. The memory will answer the request. So if it's a read request, it will fill in the data and create a reply. Then eventually the request, the reference returns to the slave transactor. And now what we can do is we can restore our original Gem5 packet by removing the extension from the generic payload. Now we can update this packet with the metadata from the generic payload so that we have all the information that the memory filled in into this payload. And now we can again we can destroy the generic payload, and then we can simply follow the Gem5 procedure and return this reference as a response to the CPU. And this is basically how it works. It works similarly for the other way around. So when we want to communicate from systemc to Gem5, then we create a Gem5 packet, and we hook the original generic payload as a sender state to the Gem5 packet. Okay, so how can you use it? So first of all, I recommend you to have a look at the examples that we created, and you can find them in the utils TLM directory of Gem5. So there's the example which I just showed you, Gen5 CPU connected to system C memory. And we also have an example for the other way around, where we have a master and system C connected to a memory in Gen5. There's also an example that uses elastic traces. And we also have a full system example, which boots an operating system in a system where the memory is simulated in system C. Yeah, just quickly about the general flow of when you want to use on the binding. So what you need to do is you will need to compile Gen5 normally, and you will also need to create a library of Gen5. And then you need to create a system C project, which uses your system C modules as you like, and that also instantiates some of your the Gen5 modules, like the transactors and the sim control. Then you simply compile your project, and you need to link it against the Gen5 library. And then the last thing that you need is a configuration for Gen5. And for that, you simply run Gen5 normally, providing some Python script. And what you get then is an config.ini file. And this config.ini file, so you need to hand to the Gen5 sim control, and then this object will be able to create all the Gen5 objects and will instantiate the Gen5 subsystem and start your simulation. So I have some more detailed view here for the slave example. So just quickly to show how a memory could look in system C. Yeah, I think it's not too interesting for now. Basically, what you do is you define some socket for the communication. You need some storage. You have a constructor written in a special way, following the system C standard. And then you also need to define your TLM interface that implement the communication. And apart from your actual memory, you also will need to define your top level in the system C world. So this is the system C main, which instantiates some system C modules. So what we need is the Gen5 sim control module. We also instantiate a transactor and then the memory. Then we bind them together, so we perform all the connections, and then we simply start the simulation. That's all we need to do. Yes, so there is some stuff hidden in these config nodes. So what is also very important is that you need to pass the config.ini file, so the path to this file, somewhere to the sim control module. Then we also need the other part. We need to configure Gen5. So this is from the TLM example, the Python script. And again, it's a very simple script that just creates a system. It creates a traffic generator CPU. It creates a crossbar bus, connects them, and it also creates an external slave and connects it to the bus. And then again, it starts the simulation. Okay, and so how to run this? First, we need to build the project. For this example, it's quite simple. There's a sconce script for that, so we simply need to run sconce. Then we need to generate the configuration file. For that, we run the normal Gen5 with our Python script, and we'll get a configuration file. And then we run our project, our binary that we generated from the system C code, passing the configuration file that we just generated. And now the Gen5 sim control will build the Gen5 system, instantiate all the objects, and we'll see that they are connected to the right transactor. And then we get an output like this. So this shows that the simulation actually runs. So we can pass a debug flag to the Gen5, and then we see the output, and it generates requests and it receives responses. Okay, So what do we use this for? So I myself, I work in the orchestration path of the CFAD, Center for Advancing Electronics Dresden. And we are working on a programming stack for widely heterogeneous systems. Yeah, so we try to combine data flow models, data flow compilers, adaptive runtime systems, an operating system, and also model checking into one stack in order to easily deploy software to wide heterogeneous systems. And for that, we need some platforms to try our technologies on. Of course, there's real hardware, but we also need some flexible simulation platforms. And when I started to work on this, we had to decide whether go for Gem5 or go for System C. I was very fond of Gem5 at this point, but there were also strong points for System C, and in the end, I decided to do both and worked on this connection between System C and Gem5. So a system that we can simulate looks something like that. So we have a network on chip, we have several tiles, and one of those tiles could be modeled in Gem5. So we have a subsystem consisting of CPU, some local memory, bus, a data transfer unit, all simulated in Gem5, and then we connect this to a System C, and we can simply plug this to our System C NOC model. And we can even plug this into a Synopsys platform architect. So this is the system as I just showed you, and a tile then can look like such that we have our master and slave transactors. We connect this to the sim control, and then there's a fourth module, which is simply a bridge that translates the standard TLM requests to our NOC protocol. And then, of course, we can also use the trace analyzer. We can see what's happening in the system. So here we see a boot of an operating system. So P0 wants a kernel, and then it loads the binaries to the workers. And of course, you can also zoom into that and look at all the details of your TLM transactions. Okay, so that's for my use cases, and I'm going to hand back to Matthias. So he's going to explain his.
Thank you. Yeah, so when I did my PhD at University of Kaiserslautern, I worked a lot with DRAMs, and especially with 3D stacked DRAMs. So here you see an example simulation of wide I/O DRAM, where we have modeled the cores with Gem5, and we run an Android with a benchmark on it, and you can see how these cores really heat up the memory stack on top of it, and there we did a lot of research. And we do that with the DRAM-sys tool. It's written in System C. And the tool includes a DRAM power model, a thermal model, and also a retention error model, because we worked also on approximate DRAM techniques. And as you can see, for example, when you boot Linux, then this slows down the Gem5 simulation by almost 2x. And mainly the reason is because the DRAM model is much more detailed as the DRAM model in the Gem5. And therefore we could see that this coupling has a very small overhead. So what you can do with DRAM-sys, I think you saw it already in that video, but there are also some other tools like a trace analyzer which visualize the TLM transactions that are going on in the system. So here this is, for example, a DDR4 memory where you see they have 16 banks, and also you go into power down modes. These are the gray bars, and you can really analyze what's going on in the system. And this trace analyzer has also another tool which checks for JEDEC compliance. That's always cool when you implement a new memory controller architecture, that you can check that you are still compliant to the memory standards. And there are also some other tools that can generate some performance statistics for you and graphs. So that's where we use this Gem5 connection to System C very, very often. And now at my new position at Fraunhofer, we do some other stuff. We do software development and software architecture mainly. for embedded systems. And also there we use GEM5 in order to simulate embedded systems. And we are not coupling it this time to System C. So we couple it with a Java-based simulator, but we use a lot of the techniques that we have developed for System C in order to get this happen. So we have a tool there which is called Feral. And this tool is basically a simulation coupling framework. So we can connect GEM5 now to several other models. This can be System C, but can also be a CAN bus simulator or Simulink model from MATLAB. And with this kind of platform, we do a lot of development, especially software testing. So what we do with it is basically for normal software testing, you very often instrument the binary, which is very intrusive, and you can change the behavior of your program. And in this project, we instrument GEM5 instead. And we keep the binary as it is. So it's really the binary that's shipped to the customer. And that's what we do here, and we reuse techniques from the System C coupling. Okay, so to summarize, so we have now the full interoperability between GEM5 and System C, and we are fully compliant to the System C standard, and it's part of the repository. So there are some possible next steps. So some people talked to me already if it would be possible to maybe change the simulation kernel of GEM5 completely to System C and replace everything and also the connections to TLM. I think this might be possible, but it's not something that we can just do over the weekend or so. And I think another important question is, can we maybe remove the step for this config file generation and directly run that with the Python configuration? And of course, we are open if you have some other suggestions. Okay, thank you very much.
Any questions for the speaker? No? Okay, let's thank Matthias and Christian.
I'm falling. Come save me, baby. I'm calling. Come catch me, baby. I'm falling.
Andreas Brogalakis, who's a senior hardware engineer at Snellixis Solutions, and at the same time he's pursuing his PhD at the Technical University of Crete, Greece. He holds a master's degree and a bachelor's degree from University of Patras, and he's interested in the design of ASICs and FPGA systems and accelerators. And the second speaker, Nicolas Taboutsis, who's also a PhD student at Technical University of Crete, working on simulation tools for computing systems. He has joined Telecommunication System Institute at the Technical University of Crete since October 2012 as a research associate. And he has received his computer science diploma from the University of Crete in Greece again. All right, and without further ado, I'm going to leave the floor to you guys.
Thank you. Hello, good afternoon. So I'm Andreas. Thank you for introducing us. This is Nikos. This is a joint work between Snellixis Solutions and Technical University of Crete. And it is based on a European-funded research project. So during the whole day, most of the talks focused on simulating a system. What we're going to talk about is how to simulate systems of systems. So the motivation behind our work was that when we're trying to build larger systems, we cannot ignore the network part. There are too many interactions, there are too complicated communications, and there are so many optimization opportunities that we cannot ignore either component. The problem is that the tools that are available, they either deal very well with one of the two, either the processing part, a processor system, memory, and accelerators and everything, or the network part, and trying to emulate anything that does the processing. And the other thing is that most of the simulators that are available, they are single-threaded. So that means that when you're trying to simulate extensively a very large system composed of very large amount of nodes, if you don't have concurrency, then the simulation will take forever. So what is exactly COSIM? COSIM is an open framework that can simulate parallel systems. I prefer the term systems of systems. And it is a single framework. It does not consist of different pieces of software that you have to manually tie together. There's a single notion of time, and there is an accurate accounting of the processing and network interactions. It has a graphical user interface that is Eclipse-based, and is based on an IP protocol, and therefore the simulation can be made distributed. It integrates also power tools, and at the moment it's open and free. We are going to release it in the next coming period. We hope that there will be commercial support by us, and there will also be add-on packages to provide extensions. The key concept behind designing such a framework was not to throw away all the work that has already been done. And the example from today's workshop is that so much work that's been done that we have to take advantage of it in order to produce something that can be used by a lot of people, and this is what we want. And therefore, we need to use well-established processing and network simulators, and we need to be able to keep everything that has been written as part of the development effort for these simulators. Therefore, we adopt GEM5 to use as our main processing simulator, Omnet++ to simulate the framework, MacPad and other add-ons for estimating the power consumption. And what brings everything together is CERTI, which is an IEEE compliant high-level architecture implementation. In GEM5, currently, the network model that is used does support only 2 nodes that are connected through a simple wire. There is this virtual Etherlink that just simulates a wire that goes from one network interface card to the other. And the major restriction is that only 2 similar systems can be simulated, either the same ARM processors or the same x86 processors, similar, exact same configurations. And there is no way that you can have a more complex topology. So what we are trying to do is modify properly GEM5 and break this virtual wire and tap on the Ethernet interfaces, send them properly through the HLA libraries, and connect them to a network simulator that will enable us to do whatever we want with the network part. By this process, we can have an arbitrary number of nodes connected with each other. We can have a sophisticated network topology, whatever we want. We can have routers, we can have switches, we can have multiple bridges, whatever we want. Now, by breaking the systems, each system is independent. Therefore, each system can be whatever we want. One can be an ARM processor, the other can be a big little configuration, the other can be an x86 processor, whatever system we want. And last but not least, by using the high-level architecture, the communication between each Gen 5, therefore each system, is IP-based, and therefore the whole simulation process is distributed. You can either have parallel execution in a multi-core machine, or you can distribute it in a number of machines wherever you want. Now, this requires some libraries to be implemented, but also restricts the use of Gen 5 to only full system simulation, because we need an operating system and the network interface card. But at the moment, we fully support x86 and ARM processors. We have not tested for other ISAs, but I believe that there is no reason not to have support for that. And we also have to build some more updated versions for the Linux kernels that we are running. On the network part, we use the Omnet++ network simulator, and it integrates some HLA components so that it can be connected with the Gen 5 system. The challenge is that the network stack of the Gen 5 system is the full Linux network stack, but the network simulator uses some more simplistic network stack. Therefore, they are not compatible. So if we are willing to use whatever has been developed as a network model in the Omnet++, there has to be a bridge between the two, and this is what we have done. And therefore, we support everything that Omnet++ supports, and that means that you can have any kind of topology and also a lot of different kind of networks. The real issue with all these things, which sound very okay, very ambitious, is that there are synchronization issues. Gen 5 is a single-threaded application, and therefore synchronization issues do not arise. It's very easy to have everything working. But when you have different Gen 5 instances which are totally independent, maybe running on different machines and simulating different systems, then you have a completely different notion of time spread around. But you cannot do that with a system that is networked, and therefore there has to be timestamps, there has to be interactions between the systems. Therefore, we solve these issues by using the HLA architecture, which is meant to be used for connecting simulators. And we use synchronization mechanisms for two different tiers. The first one is to have a proper synchronization between a Gen 5 instance and its representation in the network simulator. And the second one is to have an overall global synchronization between all different nodes. This is a little bit, I'm not sure why it doesn't show some things. Okay, so we have the Omnet network simulator, which has a representation for each one of the nodes. There's our HLA connection between every Gen 5 node and every node in the network simulator. And therefore, we have a synchronization per node in order to properly exchange data packets between the two. And then we have a global synchronization scheme so that all Gen 5 nodes can be synchronized and have a common notion of time. Now, what do we get from all these things? Gen 5 is orders of magnitude slower than Omnet. Therefore, using Omnet has a very small impact on the overall simulation time. This example shows four systems, or a number of systems, ranging from 2 to 16. either x86 or ARM, that are connected in a single network and are simulated. In the first one shows the scaling when we're in the same machine. We have a quad-core machine, and you can see that there is almost no overhead by going from 1 to 4 nodes. As we move in it, we connect another machine through a gigabit network, which is larger, and then the messages that have to be extended have an impact on the overall performance. For ARM-based systems, we can see that the impact is far smaller than x86. I think it's mostly reflected on the work that's been done regarding on the one and the other. Apparently, synchronization does introduce a performance hit, and there is also the talk about how do we retain accuracy. So as long as we permit a free running of the Gem 5 instances, and we perform less synchronization between the different nodes, then we lose on accuracy because maybe we cannot intercept certain interactions. The finer synchronization intervals we use, we can be more accurate, but there is definitely a hit on performance. This one shows 4 ARM-based Gem 5 instances booting Linux OS, and what's the impact when we use different synchronization time intervals. This is more or less from us. I hope that maybe we have some questions or interest on what I have presented.
Do we have any questions?
Can you talk about the difference between this and
Can you talk about the difference in this method of using distributed Gem 5 and like the Gem 5 dist that's been merged in relatively recently?
Yeah, well, this is the end of almost 3-year effort. So I think that we have started quite before this Gem 5 was available to us. I'm not really familiar with this Gem 5 at the moment. I don't know if you are.
Yes, but we use Umney++, which is a network simulator. And I think that this Gem 5 cannot use network simulator. I think, but we are not.
We're in the process of completing this one, and we're just
Yes.
evaluating what exactly this Gem 5 does.
Great, thanks.
Any other questions? All right.
Yeah, I was going to, can you do checkpointing and sorry. So do you support checkpointing of your Gem 5 application, which is distributed?
Yeah. There is actually one of the reasons that we were developing the whole system was to integrate it with security tools. So we have made a lot of changes to the Gem 5 in order to have advanced checkpointing, because we were doing memory dumps and things like that, so that security tools can dump on whatever piece of hardware they wanted inside the simulated system. So checkpointing is available. Do you want to add something more?
Checkpoint is available so as to security part can stop and start each node of Gem 5 and dump the memory, change the memory, and rerun from this time each Gem 5 node.
Okay. So, but also you can change the CPU model, like which is normal in Gem 5, that you do fast forwarding and then take a checkpoint and then restore.
No, we have not used checkpoint for fast. All Gem 5s boots normally from the beginning at this time, at current time of caution.
Yeah, the checkpointing was, we didn't want to have it in order to change different parts of the simulation in order to do some things faster and slower. We wanted to add it more for the security tools that we have integrated. So we do not support at this time to change the CPU models when we're doing checkpointing.
Okay, thanks. Right, any more questions? Okay, let's thank the speakers.
Supporting efficiently and seamlessly communication and synchronization issues, and allowing fast design of any kind of accelerator. In addition, COSIM, which is the previous presentation, can be extended to support our simulation environment to simulate hundreds of nodes incorporating hardware accelerators. So our system utilizes Gen 5 full system simulator to simulate complete systems comprised of numerous CPUs and peripherals running full operating system. And Accelera, which is an open source proof of concept system C simulator, which has been approved by IEEE standard. So, about our approach, this slide describes the most significant modifications that were performed in order to expand the Gen 5 full system simulator functionality to support our novel System C accelerator. Specifically, the operating system contains the user space with the user's applications. And all appropriate libraries and kernel space drivers. So in order to incorporate efficiently our accelerator module, we have developed a set of device drivers, while an interrupt handler was implemented in order to receive appropriate interrupts from the accelerator wrapper to allow full overlap of to allow full overlap of the two sub-simulations. So Gen 5 provides a memory bus to interconnect all architecture components, such as CPUs, caches, RAMs, and input-output devices, using master and slave port. So in this work, our accelerator wrapper device was attached to the Gen 5 system using one master port, which is connected to the peripheral accelerator wrapper port in order to read and write its registers, and one slave port, which is connected to the DMA accelerator port in order to write and read large amounts of data to and from accelerator. Our accelerator device was developed in order to achieve efficient communication and synchronization of Gen 5 and the System C accelerator. It inherits all Gen 5 DMA characteristics, so that full DMA transactions utilizing the full operating system can be performed. Specifically, a core containing mixed C++ and System C code was implemented for the connection of the Gen 5 C++ functions and the accelerator System C threads. In addition, it contains a large device memory, as we can see here, to store the data in the accelerator wrapper side. Similar to simulating the DDR memory found in most of the real systems, incorporating PCI-connected FPGA and or GPUs, etc. And finally, a reference System C accelerator has been developed in order to evaluate the accelerator wrapper and the Linux kernel drivers. In more detail about implementation, accelerator wrapper consists of 8 mixed C++ and System C code functions and thread. Specifically, body dynamic memory allocation algorithm scheme is implemented similar to CUDA malloc of NVIDIA GPUs. In addition, 2 DMA engines are developed to efficiently transfer the high data volumes from the Linux driver to the accelerator wrapper, and vice versa, similar to CUDA memcopy. Gen 5 synchronization event, which is triggered at every System C accelerator device cycle, is developed. In addition, initialization and clock thread are developed to generate a reset, start, and actual clock signal of the accelerator. And finally, 2 memcopy System C threads are developed to pass the data from the wrapper device memory to synthesizable input-output ports. In addition, a reference System C accelerator has been developed to evaluate the accelerator wrapper and the Linux kernel drivers. This is a helpful guideline for designers to develop their own System C accelerators. The System C accelerator consists of a main System C thread and 2 System C functions. The reference controller scheduler, as we can see here, is the main System C thread, which is called by Gen 5's operating system application, while the user has the ability to create as many individual cores as required your System C accelerator. And finally, 2 memcopy functions were implemented in order to allow communication between wrapper device memory to internal RAMs. This slide describes the interface of our integrated system, and specifically, we can see that the 6 functions which are developed from the header side inside the kernel driver. In more detail, we have implemented 2 functions, accel initialization and accel finalization, which handle the initialization and finalization of the accelerator wrapper device and kernel driver. Subsequently, 2 functions, accel malloc and accel free, were implemented in order to allocate and free space in the accelerator wrapper's device memory using body dynamic memory allocator. In addition, Accel 3 is used to deallocate the memory which is allocated from Accel malloc. And Accel memcopy is developed so as to transfer the data from inside application, user application, to device memory wrapper. So here the user can use two transfer types, either system C memcopy host to device or system C memcopy device to host, as you can see here, so as to transfer the data from inside the application to device memory. And finally, a Accel call device function has been implemented, which actually calls the system C accelerator and employs all the synchronization mechanisms. It must be noted that both Accel memcopy and Accel call device functions have been implemented as asynchronous functions due to DMA engines used to transfer the data from the host to device and vice versa. In addition, this slide describes some essential segments that should be placed on the custom System C accelerator. The first 8 lines can be placed in the header System C file, while the remaining lines declare the actual functionality. As we can see, an internal memory of the accelerator is declared in line 2 with predefined size, while System C clock thread is utilized since it is an integral part of the synthesizable System C subset. Finally, the memcopy to device and to host System C functions have also been implemented to allow an efficient data transfer from the wrapper device memory to System C internal memory. So the user can use memcopy to device to transfer the data from device memory to internal RAMs. Then some processing and some other computation threads can be triggered. And finally, the user can use memcopy to host function to transfer the data from internal RAMs to device memory. The proposed method has been compared with the conventional manual approach, as we can see in this figure. In general, the integrated simulation utilizing a full system simulator, such as Gen5, and the System C simulator is not a trivial process, mainly due to the data exchange needed between the two standalone simulators. Based on the existing conventional flow, the application executed in Gen5 writes the data that should be fed to the System C simulator in files denoted as steps 1 and 2. Then the full system simulator has to terminate or stall its execution so that the system simulator can read the data from those files without any synchronization problem. Step 3. Subsequently, the System C simulator returns its results to the Gen5 application using output files step 4 and 5, while no notion of synchronization exists in such a file-based exchange, as you can see in the top figure. In contrary, the proposed method resolves efficiently all those issues, since the full system simulator boots the OS only once, and since it communicates with the System C simulator through programmed input-output and DMA engines, full global synchronization is supported. The efficiency of our novel approach has been evaluated using two System C described accelerators, mutual information and transfer entropy. The main reason behind the selection of those two use cases is that the complexity of the accelerator hardware implementing them depends on the number of iterations supported in each hardware core. So our results are based on a typical data size of 40K samples, while the number of iterations range from 100 to 500 from mutual information algorithm, and from 20 to 100 for transfer entropy algorithm. This table illustrates the overall simulation time when calling 10 times the System C accelerator. It becomes apparent that the proposed method is 1 order of magnitude faster than the existing conventional 5-based method in all cases, and that is because the Gen 5 simulator boosts the OS only once using our method. Furthermore, the overall simulation time does not radically change, as we can see here. In this case, since the simulation of our very small System C-based accelerators is orders of magnitude faster than the actual time needed by the Gen 5 simulator. And finally, this figure compares the overall simulation times between the conventional and the proposed method in transfer entropy algorithm using a different number of System C accelerator calls when the complexity of the accelerators remain constant. For the case of the first call, this case, our method needs slightly more time due to synchronization issues in the order of a second. However, as the number of calls to the accelerator increases, it gradually surpasses and eventually dominates over the conventional method, as you can see here. Thank you.
So we have some time for questions. Any questions you might have? Okay, I have a question. Are you planning of actually contributing all this like to the public repo, or do you plan to open source like?
Yes. On March, we had published one paper date.
Okay. But when it comes to the code, I guess it's a quite hot topic, being able to simulate accelerators. Right?
Okay. Yes. We are going to distribute on the 5 community our codes.
Right. Let's thank the speaker.